All right, welcome everyone. If you didn't catch the announcements I made a little bit earlier, they were that there are slides available for you to download and mark up on Canvas, and also that I've pushed the deadline back for homework 2 from this Friday to Monday. The rationale for that is that I'm seeing people give some honest and earnest thoughts to these problems in office hours, and I don't want to cut you short. Also, I think that I'll be getting to some topics today and Friday in lecture that actually might help with the QAM architecture problem. And it would be a shame for you to have turned that in only for me to cover it later. Okay, before I get into my spiel, which will be continuing the digital modulation introduction, are there questions from the class?
Will homework 3 still be due the Friday after?
I don't think so. I think that we'll spend today and Friday on Module 3, and we'll probably spill over into Monday, which would
Okay.
then mean all of our assignments are then Monday due.
Okay.
Okay, let's go to the PowerPoint. Okay, so on Monday, I walked you through the decomposition between source coding and channel coding. And the power in decomposing a system in this way is that you can do the two designs independently because all they have to do is interface between each other with bits. We unpacked the source encoder. We unpacked the channel encoder. What I didn't draw was this figure. I think you'll understand why. But this is a more complete decomposition of what we're going to be getting into. But I kind of wanted to scare you, but I also didn't want to scare you at the same time, so I was conflicted. And we ended on this thing to consider. So today, what I'd like to do is I'd like to run you through pretty much a design process for how to talk about or how to design a digital receiver or decoder or decider. Those are all kind of equivalent terms here. So the example, we're going to do the easiest one first, and this is called, if I get the pen, this is called binary polar signaling. And we're going to work on the detection problem. Okay, so the setup is that when we, in our transmitter, we're going to have data bits, and we're going to map a 1 bit to a pulse, which I'm going to call P of t. And we're going to map a 0 bit to the opposite of that pulse. So there's really only one waveform that we're ever going to be using here. We haven't decided what that waveform is yet, but for starters, I'm going to send a positive pulse if I want to send a 1 bit, and I'm going to send a negative pulse if I want to send a 0 bit. The other simplification that I want to make is we are going to assume what's called a distortionless but noisy channel. Okay, so what does this mean? This means that from our transmitter, we are going to send P of t into this channel, and out the other side. So the distortionless part means that what comes in is exactly what comes out. There's no wiggles in time. There's no bandwidth expansion or contraction. So what we get out the other side is what we sent in. If we send in P of t, well, sorry, plus or minus P of t, then we'll get out plus or minus P of t. But we're going to model the noise as being an additive process. Okay, so the distortionless says that if we put in plus or minus P of t, we'll get out plus or minus P of t. But we're going to add to that a noise process, which we are going to assume is Gaussian. So what does it mean for a process to be Gaussian? This just means that at every time instance, n of t follows a Gaussian distribution. Okay. And so the detection problem is at its heart in our receiver. So once we've left the channel, kind of, if you like, there's a imaginary line between the transmitter in the channel and the receiver in the channel. And so once the signal leaves the channel, it enters our receiver architecture, and it's up to us to decide what goes in that architecture. So I think allowing for the existence of a filter is a good idea. We don't know what kind of filter this is going to be, but let's assume that we're going to restrict ourselves to linear time invariant filters. And this is actually the heart of this design problem, is what kind of filter ought to go there. Let's call the output of that filter, whatever it happens to be, PO of t. And if I send in positive P, I'll get out positive PO of t. If I send in negative P of t, I'll get out negative PO of t, plus whatever the filter does to the noise process. Right, and I can do this decomposition because we're assuming this is LTI. And if I put in the sum of two signals, I will get out the sum of two signals. Okay, and so now comes I think the key to understanding a lot of digital communications, is that we are not going to be acting on this signal continuously. We are going to be sampling it. So think of a commutator that comes through once every big T seconds. So this closes every T equals big T seconds. The result we're going to call R of big T. And so this is just going to be one value every big T seconds. Well, I mean, technically it's R of T, but R of T is going to be staircase, if you like. It's going to be held, right? Once I sample at a given value, so for example, R of T might look like, we sample it here, and then at the first big T, we end up with a different sample. And then 2T, we end up with a different sample. So R of T is going to be piecewise constant. And during every piece lasts T seconds, big T seconds. Okay, and this big T, we're going to eventually end up calling it the bit time. Right? It's how much time we have to decide which bit was sent. Because if we don't make our decision within that time, the next bit is already on its way, and we start getting inter-bit interference. And so I've avoided drawing in this box because I drew it too small. We're going to take R and put it through a threshold process. And this is the heart of digital communication receiver design, is don't act on continuous time waveforms, but rather act on discrete samples. And when I say act on, I mean compare that sample to a threshold. If it's bigger than the threshold, decide 1. If it's less than the threshold, decide 0. Do you see that? So this is not all architectures have to be that way, but I'm going to impose this structure on us to say that I would like to design this filter such that I make the fewest number of mistakes. So I'm taking my time here because I usually kind of rush through this, and I think it's important that we all understand why it is reasonable to use a threshold decider here. Anyone have any questions off the bat?
Yeah, I have a question. why do we have the switch? Why can't it just go directly into the threshold?
So you could think of it that way. You could think that the threshold device takes in a continuous time signal that varies and then only decides at time instances. Like that's equivalent to what I'm trying to communicate here. Yeah.
Is is the threshold like that based on the output of the function more or less than the time? Is that why it's different? Is that the switch is based on time and then threshold is based on the output of time, like R of t or whatever signal's going in?
So what will end up happening is this ends up being a question positive or negative. So typically, and for binary polar signaling, the threshold is 0. So what we're doing is we're running a comparator where we're comparing a voltage to 0. If it's above 0, do one thing. If it's below 0, do another thing. Yeah, so a comparator is like the most basic kind of threshold device.
Okay, that makes sense. Thank you.
Mm-hmm. In general, you don't have to have a threshold of 0. So this is, I want to, I don't want to give up this idea that we don't need necessarily the threshold to be set to 0. I think an argument for why a threshold type deciding process is right is because there's only two possibilities. At the end of the day, either a 1 or a 0 was sent. And therefore, at the end of the day, either this thing is true or this other thing is true. And so the dividing line between that decision is a threshold. That's just how you would describe that. So I mentioned this kind of offhand, but anytime you're designing a system, you need to have an objective, right? Whether it be minimize the settling time, minimize the power consumed, or whatever. For our system that we're trying to design, the goal will be to minimize detection errors. Detection errors. What is a detection error? Well, if a 1 was sent, we decide a 0. We made a mistake. If a 0 was sent, we decide a 1. We made a mistake. What's not an error? If a 1 was sent, we decide 1. If a 0 was sent, we decide 0. Okay. So let's talk a little. So we're going to go back to your first introductory probability course. So let's talk about the probability of an error event. So this could be the probability that we decide 1 given a 0 was sent. Right, that's one way to have an error. Or we could decide 0 given a 1 was sent. That's another way to have an error. However, we also have to account for the prior probabilities that each of those events actually happened in the first place. So you have to multiply this first one by the prior probability of sending a 0. Right? If a 0 is hardly ever sent, then the error event of decide 1 given a 0 was sent is actually quite small. And so likewise, we have to also multiply here by the probability of sending a 1. Okay, so this is, I think, what is this called? The law of total probability is if I have an event, and I'm calling that event an error, then I split the event space into the possibilities. Decide 1 given send 0, decide 0 given spend 1. Okay, so if I how do we make these decisions? Well, okay, first off, let's give some names to these probabilities. These two are the priors, prior bit probability or likelihoods. Prior because they happen before any of this deciding or transmission occurs, right? They happen a priori, if you like. And fair warning, almost all of the time, we're going to assume it's 50-50. Because in almost every instance, the data that you're trying to communicate is going to be mostly bit balanced. Okay, if it is truly a random bit source, then they will be 50-50 ones, 50-50 zeros. So usually, oh gosh, sorry people. Usually 0.5.
Do actual messages tend to be bit balanced?
Actually, yeah, and if they're not, there's actually incentive to try and balance them. Just because if you have a balanced signaling system, then if you end up sending more ones than zeros, then you're actually going to end up with a DC offset, which if your machinery is AC coupled, that ends up getting lost. So there is actually like a circuit motivation for, if you don't have a equal distribution of bits, to make to somehow make them equal before you try and send them. It's also a fun exam problem. If all your students ever do is assume that they're 50-50, then on the exam ask what happens if it's 70-30, and then watch people break down. Okay, so how do we, who decides? What does it mean to decide a one? Well, that's where we're getting at the threshold, and if R of t is bigger than the threshold or less than the threshold. So let's put the threshold at A. So if we set the threshold device so that R of big T bigger than A means decide 1, and R of big T less than A means decide 0. Now we can all of a sudden decide, put some numbers to these decision probabilities. Okay, so the probability that I decide 1, I'm going to start abbreviating here, decide 1 given send 0 is the probability that R of big T is bigger than our threshold, given negative P of T was sent. Right, so if I condition on a 0 being sent, then that's where I'm up here with this initial definition, that 0 bits on the transmitter get mapped to negative pulses. Okay, so and then we have an expression for R of t. R of t is going to be negative P0 of big T plus N of t, N0 of t. How did I know that was a negative? Because over here in the diagram, it's a plus or minus. I'm using my conditional information, my given information. If we condition on a 0 being sent, then the pulse that was sent was negative P, which means that the output of the filter will be negative P0.
Oh, is that a P?
Yep.
Okay.
So let's see. Actually, why don't you do the following? Tell me, what is an expression for a probability that we decide 0 given a 1 was sent? I'll give you a couple minutes to work that out.
Well, it's just like literally the opposite of what you wrote.
Pretty much the opposite of everything I just wrote. Yeah. So this will be the probability that positive P naught of big T plus N naught of big T is less than A. Okay, so now that I've used my conditional information, this is the same as the probability that P0 of big T is, well, minus A is less than N0 of T. So again, I'm using the conditional information to decide the SIGN in front of this signal. And so once I've done that, there's no more use to carry around that conditional information. And so then I just rearrange the arithmetic inside of the probability argument. Another way to write this is the probability that the filtered pulse at the end of the bit period is less than some random number.
Clay, quick question.
Go ahead.
Why does the sign of noise not change?
Because the noise doesn't know what pulse we sent. The noise is just the noise, whether we send a positive pulse or a negative pulse. We are assuming that the noise is going to be uncorrelated across time. And so the noise won't change. The noise process itself has to be independent of the pulse that we're sending.
So by that definition, does that mean that you'll get the same outcome regardless of the sign of noise?
I'm not quite sure I follow. Let me talk for a little bit longer, and I think I might address your question, even though I'm not sure what your question is.
Sure.
And I think we'll get to it right now, because this quantity, and then by extension, this entire right-hand side, is a random variable, which will have a distribution. And so we're asking, what is the probability that a number is less than a certain value of a random variable? So if, okay, maybe we should go to a new slide here. We're going to run out of room here real quick. Yeah, there we go. So if the noise process is Gaussian, that means that the noise process at every time instant is Gaussian. And the typical assumption is that the noise has 0 mean and perhaps some value of variance sigma squared. Okay, so we are enforcing an assumption that the noise has 0 mean, and that's well borne out, that if you take noise measurements over a long period of time, you're not going to see a DC drift over time. Okay. So if the noise process at capital T follows a Gaussian distribution, then let's see how well I can draw this bell curve. The answer is moderately. So this is, I'm sketching the probability that n, sorry, lowercase, n of t as a function of x. So what this curve represents, this is a probability density function, and to refresh your memory, this is the probability that the random variable, which we're calling n of big T, takes any value on the horizontal axis. Okay. What if I were to shift this random variable by a fixed and deterministic amount, say by a? What would I do to its distribution? So if this is the distribution for Pn of t, what does the distribution look like for P of the new random variable, which is the old random variable plus a deterministic offset?
Just a shift, right?
Yeah, so now instead of being centered at 0, this is now an A mean. Sorry, that's a terrible grammar. This is now a random variable with mean A and variance sigma squared. So whatever A happened to be, we now get a bell curve, the same bell curve, centered around A. Okay, so forgive me, I'm going to switch back to this slide one more time. We're interested in the probability that this random variable is greater than a certain value. So how would that be illustrated here? Well, we'd have to illustrate the value somewhere on the horizontal axis. And then the probability is then this area. Right, so this area is the capital P probability that the random variable n naught of big T plus A is greater than the number P0 of big T. So I've used the letter P about 18 times in this lecture already, and they mean slightly different things. This is the capital P probability that this random variable is greater than the number, which is the filtered pulse evaluated at capital T. Clear as mud? So this was not the only probability that we had to be concerned with, right? This is not the only way to get an error. So one more time, I'm going to flip back. We're also interested in this guy. So the probability that negative, actually, can I copy? This will be fun. Copy. Oh, nice. Oh, that's great. Ish. We're also interested in the probability that this other random variable, so this is the capital P probability that, how would this look? Negative P0 of t is bigger than a minus n0 of t. Which is the same if we multiply both sides by -1. P0 of big T is less than n0 of big T minus a. All right, so allow me to introduce one more color, and that would be to illustrate the PDF of this random variable, which I'll point out, and this might get at Nathan's question, this is the same PDF, but shifted in the opposite direction. Yeah, so this PDF, this random variable does not know that a 1 or a 0 bit was sent. It's the same PDF, and I think that's crucial to this analysis. And Nathan, let me know if that was not what you were getting at. So in orange here, we have the PDF of the random variable n0 of t minus a as a function of x. So this would be negative a, yeah. Okay, so we're now looking for the probability that this random variable is bigger than a fixed value. Okay, so I'm going to have to extend this orange line quite a bit. So these two have to cross at the same point, and then this tails off forever, like that. And then in this little bitty region here, this is the capital P probability that n0 of t minus a is greater than the same number, p0 of big T. So that's all a little bit cumbersome. Let me call that area, let me define that area, area 0. And let me define this area as area 1. And so I think what we started with actually was the probability of error is going to be area 1 times the probability that a 1 was sent, plus area 0 times the probability that a 0 was sent. Okay, so if the priors are equal, then the error probability is simply half of this sum. Because they're both 50-50, you factor out a 1/2 and you get the area 1 plus the area 0.
Does area 1 include area 0, or is it excluding?
It would include. Yeah. Which is actually the next point. But I'll pause here for questions because I think that combination of my writing being messy and me springing probability on you probably means there are some questions lying out there.
Is there any chance you could go over the shifting of the PDF? I think I kind of got lost there.
Sure. So let me do an aside on that. So if I have a random variable x, then the common way to write the PDF is the probability, oh my God, that random variable capital X takes value little x. Yeah, so this is a function of little x. And let's say it's a uniform distribution. So this is probability that the random variable capital X takes the value little x. And there are all these rules for PDFs, right? That their total area has to be 1, they can never go negative, all that other business. But if I define a new random variable, y is x plus 1, that is the word new there, then the probability that y takes any particular value is the same as the probability that x takes that value less 1. Right, so the probability, oh my gosh, probability that y equals 5 is the probability that x equals 4. Right, because y is just an offset from x. And so this is the motivation for why the PDF of y, so p sub y of little case y, is simply a 1 shifted version. So if this is 0 to b, this is going to be 1 to b plus 1. So this is a property of random variables. If you add a deterministic number to them, then you shift your PDF to be centered or over by that deterministic number. And I'm stressing deterministic is because the result is drastically different if you're adding 2 random things. Does that help, Omri?
Yeah, that makes sense. Thank you.
Okay, so we actually have a couple of degrees of freedom in this problem. So far, we haven't decided what our threshold should be, or we haven't decided what the optimal A value is, and we haven't decided what the optimal filter is. We have just kind of left that as some system that translates P plus N into P0 plus N0. We'll get to the filter probably on Friday, but well, we'll definitely get to the filter on Friday, but I want to address what the threshold ought to be, irregardless of the filter choice. And the argument that I'm going to make for, oh, go ahead.
Sorry, really quickly. You have a word, a sentence, if something are equal. What's that something?
That is the word priors.
Oh, okay, thanks.
Yeah, if the priors are equal. That is, if a 1 and a 0 bit were equally likely from the get-go. Okay, so if I make the threshold value A larger, so if I were to make A a larger positive number, right, because we just kind of threw an A at the screen here. If I were to make A larger, then what would change? The blue curve would move farther to the right. The orange curve would move farther to the left. But you know what wouldn't change? P0 of t. Right, because the filter output doesn't know what the threshold value was. So by increasing A, so to A prime, look what I've done to area 1. I admit I have made area 0 smaller. I have gone further into the tail of this bell curve, but I have gotten a whole lot of area here. Okay, so my argument is that the amount of area I picked up in A1 prime is more than the area I lost in A0 prime, which you can't even see because it's so small. Now, so I guess I'm bringing this up to show you that it's a bad idea to increase the threshold more than what we had before. And that's because we end up getting a whole lot of area, and area in this case is bad, right? Because the probability of error is a bad thing. So we want to minimize it, so I want less error, less error and less area. So the argument goes, make the threshold smaller. In fact, make the threshold 0. Because if the threshold is 0, then what I can do is both bell curves merge, right? Because if I'm shifting both bell curves by the same 0 amount, I get the same bell curve. And then orange is on top of that. Now, area 1 equals area 0. So area 0 double prime is equal to area 1 double prime. And my argument, and I have not proven this, my argument is that this is the sum of these two areas is the smallest possible for any given filter. Okay, so if I fix the filter, then I fix the shape of P0. I also fix the shape of N0. So all of those numbers are then fixed. And then I have to decide where should I put my threshold? And the idea is if I put that threshold dead center, i.e. a positive or negative decider, then I can push whatever P0 happens to be as far into the tails of both bell curves as possible. And the area in the tails of these bell curves are small for any given variance. The further you go into the tails, the less area you have. Questions on that? Okay, I like this because you start with like, oh, look, we can have an arbitrary threshold, and then it's like, oh, actually, 0 is the way to go. You just want to decide positive or negative. Let's see. I think, do we have time for the rest of this? Yeah, I think we do. So because the question of bit error is one of areas under Gaussians, I think we should talk about Gaussians for a little bit. Okay. So I hope it's not a surprise that if you have what's called a normal Gaussian, this is typically 0 mean and unit variance. That's what we mean by a normal Gaussian, often written just script n 0, 1. Then the probability distribution function is written like this. So it's an exponential where the tails fall off as the square of the argument. And the definition of a PDF is simply the probability that the random variable takes the value at any value in the domain. Okay. So if we are interested in areas under Gaussians, then one way to look at them is what's called the cumulative distribution function, or CDF. So this is typically written capital F of x as a function of x. And so if you're talking about cumulative distribution, then you're looking at the integral from -infinity up to x of the PDF of 1 over root 2 pi e to the minus, and this is so frustrating to me, that actually both of your textbooks, both the Agbo book and the Lothian Ding book, they don't use dummy variables here. And Agbo's book especially, I think he writes this, which is slightly maddening to me, because look, that's your independent variable and that's your dummy variable, and they are they are different things, so we should give them different names. Okay, so forgive me, I'm gonna call the dummy variable, what do you want? Let's go t. Right now it's clear that if I set the little x value here, then I'm setting the upper limit of integration. What am I integrating? I'm integrating this function, the area under this function from -infinity up to x. Okay. So the other way to think about this, and this is, think of this as probability that x is less than a certain value. In communications, what is often more important is the probability that a random variable is greater than a certain value. Okay, so we're going to not deal as much with CDFs as with what's, I don't know, unoriginally called Q functions. So Q of x is defined as the integral from x to infinity of the normal PDF as a function of a dummy. So px of y dy. Now, many of you will see that if I am looking at this area, I know that the total area is 1, and so if I take 1 and I subtract this area, I can get the area in the upper tail. So don't forget that there's a quick mapping between these two. That the Q function is simply the complement of the CDF. And I spent some time on this because when I took probability, we talked about PDFs, we talk about CDFs, and so in my mind, all these CDFs are monotonically increasing functions, right? If I go further along the number line, then I have more things the random variable could be, so the cumulative distribution has to go up. All of our relevant calculations in communications are going to be how far into the tails are we, which is often translated into the Q function, which is the exact opposite of CDF, right? So as I move the argument higher up the number line, the Q function diminishes because the area diminishes. Okay, so I spent some time on this because I myself have to constantly remind myself that Q functions are monotonically decreasing and CDFs are monotonically increasing. Okay, I think this is a good place to stop because I have one more kind of Gaussian-like quantity to talk about, and it's really fun to say it's the ERF function and its close cousin, the complementary ERF function, ERFC. All right, I can tell you got bated breath. But yeah, we'll talk about ERF and ERFC on Friday. Thanks, everyone.